All right, starting video number 2 here. It's going to be very small. So again, looking at simplifying things, 6.00 square root of 3 over 2 times v1f plus v2f cosine 60 is a half. Here I have 0 as v1f, sine of 30 is a half, minus, and now the sine of 60 is the square root of 3 over 2. So they flip-flop. So square root of 3 over 2 times v2f. So I have 2 equations and 2 unknowns. What's nice is that, so I'm going to kind of rewrite these a little bit. So again, remember those original nasty ugly equations? Well, this is what I'm down to now. Because I made some assumptions, I know what my angles are, so on and so forth. All right? So, what do I have? Top equation, square root of 3 over 2, v1f plus v2f over 2 equals 6.00. And the second equation is going to be v1f over 2 minus the square root of 3 over 2, v2f equals 0. All right, so again, nice and simple. What I can actually do is I can actually simplify stuff a little bit, or well, what I can do is I can take the second equation and write it in terms of or one variable right in terms of the other, and then substitute. So the second equation sets me up very nicely to do that. So what I'll just do is I'll take the second equation and I'll just solve for v1f. So looking at this equation, I'll say, well, I'm going to multiply through by 2. No problem there. So v1f minus the square root of 3 v2f equals 0. Or I can simply write this as v1f equals the square root of 3 times v2f. Again, no big deal there. And what's the next thing I want to do? Well, next thing I do then is I'll substitute. So I'll substitute into the other equation. Okay, so the first equation would then become square root of 3 over 2. What's v1f? Well, v1f is the square root of 3 v2f. Instead of v1f, I'll just write the square root of 3 v2f. Then I have the second term plus v2f over 2 equals 6.00. All right, and so I'm going to do a little erasure here. Square root of 3 times square root of 3 is just 3. So I have 3 halves v2f plus v2f over 2 equals 6.00. Or solving for that, I get, essentially I multiply through by, I can 3 halves and 2 halves is just 2, right? So I have 2 v2f equals 6.00. And I get quite simply that v2f is just 3.00 meters per second. There's one of my unknown final velocities. What I can then do is simply pick one of the other 2 equations to solve for the other velocity. So remember, a few lines up, before I did the substitution, I wrote the following. So recall that I wrote that v1f is just the square root of 3 v2f. Well, I figured out v2f, right? So quite simply, v1f is the square root of 3 times what's v2f? That's 3.00 meters per second. So doing that, I get v1f is going to be 5.20 meters per second. Okay, so again, I started with the most general equations for two-dimensional collisions. And I said, well, let's be smart. I know that one of my pucks is sitting at rest. The other puck, well, let's make the x-coordinate go along with its direction. That way, theta 1i is 0. I was given a scattering angle of puck 1 is 30 degrees. I utilized this hint that the book gave that when in elastic collisions, the two actually form a 90-degree angle. The two final scattering angles form a 90-degree angle. So then I said, well, if I called puck 1 going at 30 degrees, then puck 2 must be going at negative 60 degrees. I utilized that to solve, because I had 3 unknowns, so I was able to get it down to 2 unknowns. And then so altogether, when I did this, I essentially was able, and also it's utilized the fact that the pucks have the same mass; they're identical, so all the masses cancel out. So we just kind of saw we went from the most generalized two-dimensional equations and just basically started to simplify them until they became kind of nice and simple. But you have to start off with the most generalized equations. All right. So now I have these final answers. And again, I utilized earlier on that if I'm going to assume an elastic collision, then the two are at 90 degrees to each other. Let's actually verify as one last thing that that collision really was elastic, which basically means that the energy was conserved. So I have these final velocities. So I'm going to do one more calculation to prove that the energy truly was conserved. So, let's verify that the collision was actually elastic. All right, and I'm going to do things in an interesting way. So I know that the initial kinetic energy, well, again, the first puck was not even moving, right? And I don't care about directions anymore, right? Because remember, energy is a scalar. So I just have 1/2 m1 v1I squared. Don't have to worry about angles, none of that stuff, right? And v2I was 0 because the initial puck was the second puck was initially at rest. The final kinetic energy, well, that's 1/2 m1 v1f squared, which I just got done computing, plus 1/2 m2 v2f squared. And the question is, well, I can sit there and compare the two, but there's actually kind of a cool way of doing this. And that is, if the energies are really conserved, I can form a ratio, and that ratio should be 1. So let's kind of form this ratio. Kinetic energy final over kinetic energy initial. It's kind of another way of proving things. So the final, I have 1/2 m1 v1f squared plus 1/2 m2 v2f squared divided by 1/2 m1 v1I squared. All right, and here's the thing. All my halves clearly cancel out, but remember, the pucks are all identical. All their masses are the same, right? So again, I can cancel out the masses. And I know m1 equals m2. So this ratio becomes something much simpler. It's just v1, let's write it down here. So the ratio becomes kinetic energy final over kinetic energy initial. Just becomes v1f squared plus v2f squared over v1I squared. All right, go back to my answers. V2f squared, what was that? That was 5.20 meters per second quantity squared plus, what did I say V2f was? 3.00 meters per second quantity squared. And then my initial was 6.00 meters per second quantity squared. And if I continue my calculation, I find out the kinetic energy final. Again, all these meters per second all cancel out. I get unitless number, which I would anticipate getting. I'll get 36.0 divided by 36.0, which is 1. Indeed, it is conserved. It means the total energy after is the same as the total energy before. This is truly an elastic collision. Energy is conserved. All right, that is what I have for momentum.